Okay, so differentiation by first principles anyway, look, it's literally just the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Okay? And remember, the target is always how do we get rid of the h from the bottom of the fraction. Okay, it's always in the bottom. If h is on top, don't bother you at all. It's always the one from the bottom that you're interested in getting rid of. Mainly because you can't divide by 0. Okay? Now, the homework example that I gave you was this one. If f of x equals x cubed, find f dash x. Okay, so if f of x is equal to x cubed, find f dash x. Now, according to my formula, f dash x equals the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Agreed? Which means that f dash x is equal to the limit as h approaches 0 of x plus h cubed minus x cubed all divided by h. So literally all I've done there is I've just said to myself, well, f of x is x cubed, so f of x plus h is going to be x plus h to be cubed. Okay? So x plus h to be cubed minus f of x, so that's minus x cubed, and then all divided by h. Okay? Now, have any of you ever heard of a thing called Pascal's triangle? Who's heard of Pascal's triangle? It's a sneaky way of multiplying out brackets. Okay? Basically, it gives us a quick way. So I'm going to do that over here on the right hand side. It's called Pascal's triangle. Okay? Right. You start off with a 1 on top and then 2 1s down here. So it's like a triangle with 3 1s. Okay? Triangle with 3 1s. How many of you now recognize it? Now that you're seeing me drawing it? 2 people. Right. All we do is down along the diagonal here is 1 1 1 1 1 1 1 1 1 all the way down along, and going down this way 1 1 1 1 1 1 1 1 1 all the way down along. Okay? So we continue with a 1 here and a 1 here. Now the question is, what number do we put in here? 2. Where do you get 2 from? The 2 numbers above it, this number here and this number here, you add them together, and that gives you a 2. Now to construct the next row, we've got a 1 at either end, and what goes in the middle? What am I going to put here? 3. What am I going to put here? 3. Is that okay? Now the next row, 1, 1. Fill in the bits in between. 4, be careful, 6, 4. Jenny, I actually forgot to bring my roll book, so what I'll do is I'll tell you afterwards, okay? Who's missing? Sorry, who's missing? Can't think off the top of my head. David McGrath, Chenzi, and Hodefa. Okay? So are we happy with that? 1, 4, 6, 4, 1. What would the next row be? I'm not going to write it down, but what would it be? 1, 5, 10, 10, 5, 1. Okay? Now, the question is, what's the point of this? The point of this is quite simple. I would use this row here if I was doing x plus y to the power of 1. Would you agree that x plus y to the power of 1 is 1 multiplied by x plus 1 multiplied by y? Yes? If I look at x plus y to be squared, would you agree it would be, I'll just write down the answer, x squared plus 2xy plus y squared, wouldn't it? Look at the coefficients. 1 multiplied by x squared plus 2 multiplied by xy plus 1 multiplied by y squared. So if you use this for power of 1, you use this for squaring, what are you going to use this line for? Cubing. And isn't that exactly what we're doing to x plus h cubed? Now, do you notice that the power on the first letter, x, you start off at x squared, and then you have x, and then you've no x. The power on x is dropping down, and the power on y is increasing. In other words, this is a way of cubing out a set of brackets without using the binomial theorem. Okay? You can avoid the binomial theorem. So this is going to be equal to the limit as h approaches 0. Now, isn't it going to be 1 times x cubed? Remember now, we're looking at this row here. Right? That's the row we're looking at. So it's 1 multiplied by x cubed plus 3 multiplied by x squared y. Sorry, not y. My mistake. What should I put there? H plus 3x h squared plus h cubed, and then minus my x cubed, all divided by h.
You can learn them off by heart as well, right?
The triangle?
No.
You could, yeah, you could, but it's better to have an explanation, either the binomial theorem explaining it or Pascal's triangle explaining it. Okay? Now if you look at the bit that I've highlighted in yellow, 1 by x cubed plus 3 by x squared h plus 3 by x h squared plus h cubed. The power on x is going down 1 every time, and the power on h is going up 1 every time. Is that okay with everyone in the room? Now remember, our goal is for everything on top that doesn't have a h in it to disappear, isn't it? Now what's the only thing on top that doesn't have a h? X cubed at the start, and nicely there's another x cubed at the end, the minus x cubed. Okay? So the x cubes disappear. Okay? And then what does that give me on my next line? The limit as h goes to 0. What's 3x squared h divided by h? 3x squared. What's 3xh squared divided by h? 3xh. And then what's h cubed divided by h? H squared. And all my problems have gone. The h off the bottom line has disappeared. So now it's just a matter of putting in 0 for h. So what's my final answer? F dash x equals anything with a h in it is going to disappear. So do you see those two things there? They're going to vanish. Okay? So what am I left with? 3x squared.
Can you just go over the Pascal?
I will, of course. What part of it now, Mohammed? How to build it or how to use it? How to use it. Okay, well let's say, can you see the bottom line of it? This one is for x plus y to be cubed, isn't it? This one would be for x plus y to the power of 4, because you're down another row. So let's just work out what x plus h to the power of 4 would be. Okay? X plus h to the power of 4. Right? Now look at the numbers one at a time. It'd be 1, see the 1 over here? 1 multiplied by x to the power of 4 plus 4 multiplied by what happens to the power of x? It drops 1. So 4x cubed and h appears in the game. Plus, what's the next number on the line? 6 x squared h squared. X is going down, h is going up. Plus, next, 4. Tell me what it is, Mohammed. X h cubed. And then tell me the last one. Plus 1 times h to the power of 4. Isn't it easy? Okay. Can you call out actually, what would the next line be again? Call it out to me. 1, 5, 10, 10, 5, 1. Is that okay? 1, 5, 10, 10, 5, 1. So is everybody okay with that? Martin?
When I was doing this in teaching the last school, we didn't go through all that theorem. We just said 3x cubed is just equal to 3x squared. So you have to keep writing out all of
Well, you see, you only have to do this, Martin, if they say by first principles. If your teacher was just writing down 3x squared, they were just differentiating it. If they say differentiate it, you can do it whatever way you like. And I wouldn't use first principles unless someone said that I had to. But you see, the point of what we were doing the other day is that you're told you must do this by first principles. Okay? So, yeah, I agree with you totally. If you said to me, John, differentiate x cubed, I'd shout straight back at you 3x squared. Okay? But that's not first principles. Okay? So are we all clear? You only use first principles. Like we said on Tuesday's class, you only use first principles if someone says use first principles. Okay? So do we understand it now? Literally, just during the day, will you practice building Pascal's triangle without looking at it? Okay, just a couple of times in study, a couple of times tomorrow, just start with the 3 ones and build up the rest of it. Just so you're sure you're able to do it, and refer back to this then. Okay? Right, well the other things we need to be able to differentiate by first principles will be as follows. What I want to talk about now are rational functions. What's a rational function? It's a function that's in the form of a fraction. Okay, so this is the second thing. By the way, the first things we were doing were polynomials, weren't they? Where it was just positive whole number powers of x. These are rational functions, and then the next thing after this is going to be square roots. Okay, so anyway, rational functions. If f of x is equal to 3 over x, find f dash x by first principles. Okay, so again, Martin, what does that mean? We got to go through the messy. Okay, we've got to go through the messy theory. We can't avoid it. Okay, so if f of x is equal to 3 over x, find first f dash x by first principles. Well, f dash x is going to be the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Okay? And that's equal to the limit as h approaches 0 of, now if f of x is 3 over x, there's f of x. What would f of x plus h be? 3 over x plus h. Just put in x plus h instead of x. So 3 over x plus h minus f of x, well that's just 3 over x. And then the whole shooting gallery then has to be divided by h. Is that okay? Everybody happy with that? Now, what am I supposed to do with this? How do I simplify this down? And again, just keep in mind, all the way through this game, that's the h I want to get rid of. Okay, I have no problem with this h here because it's not a h on its own. If I could put in 0 instead of that h, I'd be left with 3 over x, so that's not a problem. The problem is this one. Okay? Now, what was the way I told you before of simplifying fractions within a fraction? Multiply everything by x and x plus h. Okay? Now, what's going to happen if I multiply the first part here, 3 over x plus h by x times x plus h? I'm going to be left with 3x, haven't I? Because what's going to disappear? The x plus h is going to cancel. Now, if I do it with the next bit, what happens when I multiply 3 over x by x and x plus h? I get 3 times x plus h. Is that okay? Now, whatever you do to the top, you've also got to do it to the bottom, so I can't ignore the bottom, can I? I've also got to multiply the bottom by h, x, and x plus h. Is that okay? So everything on top and everything on the bottom was multiplied by x and x plus h. Now, again, ultimately, my goal in life is to get rid of that guy. Okay? Get rid of that. Now, not giving you a smart answer, all you do is multiply out the top line and just hope that everything on top that doesn't have a h in it disappears. So then as soon as you cancel all of the bits that don't have x's, that don't have h's, you can get rid of your h. So when I multiply this out on top, I get the limit as h goes to 0 of 3x minus 3x minus 3h divided by h, x, and x plus h. And the good news is plus 3x and minus 3x cancel out. So I'm left with the limit as h approaches 0 of minus 3h divided by h, x, and x plus h. Okay? And then what's the good news in our future? Well, got a h up here, got a h down here. Remember again, this was my problem h, this one here. Okay? And now I've got rid of it. Because when I cancel those two h's, when that cancels with that, I'm left with the limit as h approaches 0 of minus 3 divided by x and x plus h. Okay? So final answer. What's f dash x? Is there any problem with putting in 0 instead of h now? There's no problem at all, because if I put in 0 instead of that h, I'm left with x by x on the bottom, which is very simply just x squared. So my final answer is minus 3 over x squared. That's it. Is that okay? So that's how you do a rational function. Any rational function is the exact same. At some point, you're going to multiply by this guy over here, which is basically the LCM. Would you agree with that? The least common multiple of the denominators. So you multiply every part by the LCM. Everything on top that doesn't have a h in it should disappear off the face of the earth. Then you cancel your h's, and it's almost game over then. You just put in 0 for h after that point. Okay? Now, if something happens and the h on the bottom is not disappearing for you, doesn't that mean you've made a mistake? Okay? Eventually that h has to vanish. Alright? It should vanish. But are we all okay with this? Yeah? Right. Next thing is how to deal with square roots. So how to deal with rational functions? The trick is multiply by the denominator at the top and bottom, isn't it? Okay? There's a different trick for square roots. So here we go. If f of x is equal to the square root of x, find f dash x by first principles. So again, we're stopping ourselves from doing it the way you were talking about, Martin. We have to actually prove it. Okay? So f of x equals root x, and sorry, I'll put a 4 in front of it, and the 4 will actually make life easier. Trust me on that. Okay? It'll actually help me. So f of x equals 4 root x. You would call it 4x to the power of a half if you were doing differentiation by rule. But by first principles, that would absolutely not be the right way to do it. Okay, there's a different trick. It's not y's to get rid of the square root sign here. It's because of first principles. If any other situation, Adam, I'd agree with you a million times out of a million. Okay? So f dash x is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. All happy? So that's going to be the limit as h approaches 0 of 4 multiplied by, what's f of x plus h? Root x plus h minus 4 root x all divided by h. And the exact same story again. We now just need to come up with a clever way of getting rid of that h. Okay, that h in the bottom is the one that has to go. Okay? Now we're basically just going to use simple algebra tricks, and we're just hoping that at the end the thing will look nice. Okay? So here goes. That's equal to the limit as h goes to 0 of 4, I'll take out the common 4 on top, root x plus h minus root x all divided by h. So I haven't really done much there except take out that 4 on top. Now, has anybody got any suggestions as to how I could get rid of the square roots? Okay? Ultimately, I want to get rid of h, but by getting rid of the square roots on top, I will also actually get rid of h. We did this in algebra. Multiply, well done Michelle, multiply the top and bottom by the conjugate of the top. Okay? Now what's the conjugate of root x plus h minus root x? Root x plus h plus root x. Okay? But remember, if you multiply the top by that, you've also got to multiply the bottom by that to keep the account balanced. Okay? So that's going to be, the limit as h goes to 0 of 4 multiplied by root x plus h minus root x multiplied by root x plus h plus root x, the conjugate of the top, divided by h and also root x plus h plus root x. So whatever you do to the top, you've also got to do to the bottom. Okay? So that's equal to the limit as h approaches 0 of 4 multiplied by, anybody spot anything on top? It's the difference of two squares. You're creating the difference of two squares. So on top, isn't it root x plus h squared minus root x squared, isn't it? And then all divided by by root x plus h plus root x. Don't multiply at the bottom, the brackets on the bottom, it's of no advantage. Okay? Are we all happy with that? That's the difference of two squares. The only difference between the two brackets is the plus and minus in the middle. Now, everybody in the room knows what squaring does to a square root sign. Cancels it out, doesn't it? So what's the square root of x plus h squared? X plus h. So that's equal to the limit as h goes to 0 of 4 multiplied by root x plus h to be squared is just x plus h, and then root x squared is just x. And that's all divided by h multiplied by root x plus h plus root x. Now on top, the good news is plus x and minus x cancel out. And that means that effectively then on top we're just left with 4h, aren't we? But then the h that I've been trying to get rid of all this time is about to disappear. So that's the limit as h approaches 0 of 4h divided by h by root x plus h plus root x. Okay? H on the bottom, h on the top cancels out, and I'm left with the limit as h approaches 0 of 4 over root x plus h plus root x. Okay? Everybody happy with that? All I've done on that last line is just cancel the h's, nothing more. Now, up to now, I've had a serious problem with putting in 0 instead of h. This h on the bottom has prevented me from doing it. Now, I still have a h underneath on the bottom line, but is that h a problem? This h is not a problem because it's not on its own. It's h plus x. Okay? So if I put in 0 there, I get root x. I don't get 0. Okay? So when I put in 0 instead of h, are we all agreed? I get 4 divided by root x plus root x. Yes? So f dash x, I'll simplify it a little bit more. What's root x plus root x? 2 root x. Well, we have a 4 on top, so the 4 on top is going to cancel with the 2 on the bottom, and you'll be left with 2 over root x. Alright, so you can see there's just a little bit more work involved when you're differentiating a square root sign, isn't there? And as I said, the main step is...
Sorry, John.
Yeah, no problem.
Just 2 seconds. Can I just remind you? CAO, early application.
Right, so f dash x anyway, 2 over root x. Well, you see, if you look here, it's 4 divided by 2 root x. Because you have root x plus root x, and 4 divided by 2 gives me the 2. Okay? Now, worst case scenario. I'm going to give you about a 30-second head start and let you kind of try to work ahead of me on this. If f of x equals 1 over root x, find f dash x by first principles. Now, I'll give you a little bit of a hint. It combines the problem we had with fractions with the problem we had with square roots. So it's kind of the two problems put into one question, which makes it a prime contender, doesn't it? Okay? Anyway, as I said, I'll give you a few seconds of a head start. what should the first line be? 1 over root x plus h minus 1 over root x, and then all divided by that annoying h on the bottom that we need to find a way of getting rid of. Okay? We're at nothing. The limit doesn't exist until that h disappears. Would you agree? So at the moment you think the limit is infinite, wouldn't you? Okay, so until we get rid of that h, we're in bother. Well, advise me on the next step. Yep, so what am I going to multiply by? Root x and root x plus h. Whatever you see that's appearing underneath the division line. Okay? Now, what happens if I multiply this bit here by root x and root x plus h? I'm just left with the root x because root x plus h disappears, doesn't it? So that's going to be the limit as h approaches 0 of root x minus, well, now this bit. What's going to happen when I multiply 1 over root x by root x and root x plus h? I'm left with root x plus h. And then if I multiply the top, I also have to multiply the bottom. People very often forget that. So h root x multiplied by root x plus h. Is that okay? So we've used our rational functions trick, haven't we? Multiplying top and bottom by the least common multiple. So now it comes down to how do we get rid of square roots off the top? So we use our other trick, which is multiply by the conjugate. Okay? So I'm going to multiply the top and bottom by what? What do you mean conjugate? So the limit as h goes to 0 of root x minus root x plus h multiplied by root x, as you said, plus the square root of x plus h. And then that's all divided by, now the bottom line is going to look terrible for a minute. H root x plus h, that's already there. And now we're also multiplying by root x plus root x plus h. Is that okay? So we've multiplied top and bottom by the same thing. So the bottom at the moment looks like a bit of a mess. Alright, but anyway, there's very little we can do about that. Now on top again, same as before, it's always going to be the difference of two squares. Okay? So what will the top line simplify down to? Limit as h goes to 0 of, what's the square root of x squared? X. Minus, what's the square root of x plus h squared? X plus h. And then divided by h root x plus h multiplied by root x plus root x plus h. Okay? Now what's going to happen on top? Yep, I've got a plus x here and I've got a minus x here, so they're going to disappear. So the only thing left on top is what? Minus h. Okay? Minus h. So that's going to be the limit as h goes to 0 of, now my minus h on top, the h is going to cancel with that little h on the bottom. The only thing I'm left with on top is minus h. So minus h divided by h is going to cancel to just give minus 1 on top, isn't it? So that's going to be minus 1 divided by root x plus h, and then root x again, plus root x plus h. Okay? Now, next step. At this stage, can I put in 0 for h? Absolutely, yes I can. Okay? The h's on the bottom now are not on their own, they're with x's. So if I put in h here instead of the first one, this one here, I'm not going to be left with 0, I'm going to be left with x, root x. If I put in 0 for h there, I'm also going to be left with root x. So that means that f dash x equals minus 1 divided by root x times root x plus root x. Happy? Because obviously when I get rid of the h here in the brackets, I'm left with root x plus root x, which is going to be on the next line, 2 root x. And also, would you agree, this is the first time that I've dropped the limit as h goes to 0, because I've actually put in 0 for h. So this is minus 1 divided by, are we agreed that root x multiplied by root x is just x? Now what's root x plus root x? 2 root x. So you could say that f dash x equals minus 1 over 2x root x, and that would be perfectly right. Okay? Minus 1 over 2x root x. Well, what would you say if the examiner said, write your answer in the form a over bx to the power of c, where a, b, and c are elements a, b, c, are all elements of q. What's q? Fractions, rational numbers. Okay? So now they could be whole numbers. By the way, all whole numbers are also rational numbers. So some of them are whole numbers, but there is one of them that's going to be a fraction. Because you see on the bottom line, isn't it minus 1 divided by 2x to the power of 1 multiplied by x to the power of a half? Yes? A square root means to the power of a half, as we know from algebra. So f dash x equals minus 1 divided by, what does multiplication mean? What do you do to powers? Add the powers. And 1 plus a half, that's x to the power of 3 over 2. Okay, now if they just say differentiate by first principles, if you left your answer like this, you get full marks. If you left your answer like this, you get full marks. Now if they said use first principles to prove that f dash x can be written in this form, well then you have to keep going until it's in that form. Is that okay? We all alright? To be honest with you, I think when June arrives, I think you'd all be absolutely delighted if you saw first principles appearing on the exam. Okay, I think you'd be absolutely thrilled. It's not the hardest thing on the course by any stretch of the imagination. Because once you learn the tricks about getting rid of the h on the bottom, the rest of it is just straightforward. With polynomials, you don't really have to do anything other than square them out or cube them out or whatever, because the h will just naturally disappear. With fractions, it's always multiplying by the LCM of the denominators. And then with square roots, is always multiplying by the conjugate. And then that last question was a mixture of fractions and square roots, so that's kind of as hard as it gets. Okay? So we're all totally happy with it? Okay. Now, Martin, as you said earlier on, you'd want to be mad to do it this way, unless someone said to you, you must do it by first principles. Okay? Generally, we just use a thing called differentiation by rule. Okay? So let's look at that. Now, today we'll just get to mention it. Tomorrow we can kind of get a little bit deeper into it. So differentiation by rule. Now, unfortunately, first of all, I don't like using rules unless we prove them, so our first rule, we're going to have to prove it. Okay, that if f of x is equal to x to the power of n, then f dash x equals nx to the power of n minus 1 for n an element of n. There's a hint in the end of the question there, isn't there? What's the little hint? For n an element of n means for n a natural number. So really what they're saying is that when you're differentiating a power of x, you just bring the power down in front and reduce the power by 1, simply. Now, we're only going to prove it for natural numbers, but it works for fractions and decimals and any kind of number. Okay? But we can only prove it for natural numbers because it's the only thing that we're able to use induction for. Is that okay? We're going to prove it by induction, but for natural numbers only. You just assume, take my word for the fact that it works for integers and fractions and decimals and any number you care to think of. Okay? So, think induction. What's step 1 of every induction proof? Prove true for the lowest value of n. So, is in my step 1 here going to be prove it's true for n equals 1. Now, usually proving true for n equals 1 is a matter of course. It's simple, isn't it? You actually have to do something. This time it's not straightforward. So, step 1. Prove true for n equals 1. Because you see, if it's not true for n equals 1, there's no point in continuing. Okay, it means it's false completely. And anyway, that's the basis of our theory, isn't it? It's the basis of our induction hypothesis. So here goes. If f of x equals x to the power of 1, here's what I'm wondering. Is f dash x equal to? If it's true, what should happen? What should f dash x be equal to? Shouldn't it be 1 multiplied by x to the power of 0? Bring the power down in front and reduce the power by 1. And anything to the power of 0 is just 1. So if this is true, f dash x should be equal to 1, shouldn't it? Yes? Now the only thing is, at the moment, it's just a hypothetical question I'm asking myself. It's not, I don't know that it's true yet. To prove it's true, I got to use first principles. So, let f of x, we'll just let f of x equal x, because isn't that basically x to the power of 1? Isn't it? So f dash x, we know for definite anyway from first principles, that f dash x is going to be the limit as h goes to 0 of, what's f of x plus h if f of x is equal to x? X plus h. Minus f of x, isn't that just minus x? All divided by h. Plus x minus x cancels out. So that's the limit as h goes to 0 of h over h, which is the limit as h goes to 0 of 1. Because the h cancels with the h. What happens now if I put in 0 instead of h?
If you didn't need to put that limit as h goes to 0, before 0 instead of h.
Well, I can't, while I can still see that h on the bottom, I can't put in 0. It's only now that it's disappeared that I can really, Mohammed. I shouldn't jump in and put in 0 too quickly. But is everybody in the room agrees that the answer is definitely 1? So what's the moral of the story? It's true for n equals 1. We wanted 1, we got 1. Okay? So it's true for n equals 1. Now, what happens next? We assume it's true for n equals k. So step 2, we assume true for n equals k. So what are we assuming? We're assuming that if f of x is equal to x to the power of k, then f dash x equals k multiplied by x to the power of k minus 1. We're assuming the formula works. Okay? Now, like every other induction question, would you agree we're not going to get out of jail without using that assumption again? Okay, that's not the last time we've seen it. We will definitely be using that again at some stage. So if f of x is equal to x to the power of k, we're now going to assume that f dash x is equal to kx to the power of k minus 1. So the formula works for k. So here's the juicy bit. What do I have to do? Prove true for n equals k plus 1. Okay? Now I have to say, I have to use a small thing that I haven't done yet with you to do this, but it's something I'm sure you've all done before at some stage, and that's the product rule. Okay, I just have to use it. Don't worry, we'll be using it every day, 10 times a day within a couple of days' time. So at the moment I'll just write it down, and then we can use it properly. So here's what I'm trying to prove. If f of x equals x to the power of k plus 1, show that f dash x equals k plus 1 multiplied by x to the power of k. That's what I'm trying to show. Alright, that it still works, that I can bring the power down in front and reduce the power by 1. Now, at the moment, this is wishful thinking. I have to show that it's actually true. Okay? So here goes. Let f of x equal x to the power of k plus 1. Now, we're always in induction, we're trying to find a way of bringing in our assumption, aren't we? So would we agree that x to the power of k plus 1 is simply just x multiplied by x to the power of k. Isn't it? It's x times x to the k. Yeah? Now, the product rule, this is the bit that I haven't done yet, but it's only tiny. Product rule, you use it when you've got two functions multiplied together, don't you? And what have I got here? I have x multiplied by x to the power of k. So over here on the right hand side, we'll use our product rule. So function u, we call them u and v. U is x, and v is x to the power of k. Now f dash x can also be called dy dx, can't it? So if u is equal to x, what's du dx? 1. Now we can't just say it's 1, we need to say from part 1 of our proof. The first thing we proved was that it was true for n equals 1, that if you give me x and differentiate it, you get 1. So I'm not pulling that from the sky, we proved it in step 1. dv dx, what's that? Kx to the power of k minus 1. Why? By my assumption. My assumption is that that's true. That if I differentiate x to the power of k, I get x to the power of k plus 1. Okay? Now, what is the product rule? Absolutely. The formula is u dv dx plus v du dx. So for the first bit, what two things am I multiplying? U dv dx. U dv dx, I'm multiplying x by kx to the power of k minus 1. So u is x and dv dx is kx to the power of k minus 1 plus v du dx, isn't that x to the power of k multiplied by 1? Isn't it?
When did you become minus 1?
Well, from my assumption. You see, my assumption, Sean, was that if f of x is equal to x to the power of k, if you differentiate x to the power of k, you get kx to the power of k minus 1. So here we have an x to the power of k, and I'm just saying if you differentiate that, you get kx to the power of k minus 1. So I got it from step 2 from my assumption. Okay? Now, what's x multiplied by x to the power of k minus 1? It's x to the power of k. Like, think about it, it's like as if there's a power of 1 here. And multiplication means add the powers. Now what's 1 plus k minus 1? K. Alright, so that's absolutely true. And then over here it's just x to the power of k. Would you agree that I have an x to the power of k here and I have an x to the power of k here? So couldn't I take out that common x to the power of k? And I'd be left with k plus 1 by x to the power of k. Are we all agreed on that? Just taking out the common x to the power of k. I've got an x to the power of k multiplied by k here, and I have an x to the power of k multiplied by 1 here. Take out the common x to the k, and you get k plus 1 by x to the k. And the good news is, look up here, and look down here. What do you notice? What we wanted to get, we've gotten. Is that okay? Oh, sorry, looked at the wrong one. Sorry, this one here. K plus 1 by x to the power of k, k plus 1 by x to the power of k. We got exactly what we wanted to get. So what's the consequence? What's our conclusion? How do we phrase it again? Do you remember? The statement is therefore true for n equals k plus 1. Sorry, if it is true for n equals k. Agreed? And then we say, well, go back to step 1. It was true for n equals 1, wasn't it? So we say, since it was true for n equals 1, it will also be true for n equals 2, 3, 4, etc., and so on for all n an element of n. Okay, you see the thing is, in step 3 we proved that if it's true for k, it's true for k plus 1. So if any domino falls down, it's going to knock down the next one. Okay? But you see the first domino fell down, so that's going to knock the second one. But now the second domino is falling down, so that's going to knock the third one. Now the third is falling, that will knock the fourth. And this goes on forever. Okay, so the conclusion is that the statement is true for all n an element of n. Okay?